The Polymer Century, an industrial and economic history of the plastics age, 1860 to 2024. This review presents an exhaustive industrial and economic reconstruction of the global plastics industry, tracing its evolution from the artisanal semi-synthetics of the Victorian era to the petrochemical hegemony of the 21st century. By synthesizing data on production technologies, capital expenditure, CapEx, and geopolitical strategy, this analysis argues that the history of plastic is not merely a history of chemistry, but a history of industrial sovereignty. It details the transition from the scarcity-driven inventions of celluloid and bakelite to the state-sponsored autarky of the World War II synthetic rubber and nylon programs, which established the template for the modern industrial complex. The narrative then examines the post-war golden age of disposability, driven by the advent of the reciprocating screw and the polyethylene explosion, before analyzing the seismic shift of production centers to Asia under initiatives like Made in China 2025. Through a rigorous examination of cost structures, resin pricing volatility relative to oil shocks, and the technological displacement of traditional materials, this review offers a unified economic theory of the plastic age, documenting an expansion of 1.5 million tons in 1950 to an estimated 460 million tons in 2024. The origins of the modern plastics industry are rooted not in the abundance of fossil fuels that characterizes the 21st century, but in the acute resource scarcity of the 19th. As the Industrial Revolution matured, the Western world faced a critical shortage of natural materials essential for the burgeoning consumer class. Ivory, tortoiseshell, and horn, materials harvested from living creatures, could not scale to meet the demands of mass production. The most acute crisis emerged in the supply of ivory, the preferred material for billiard balls, piano keys, and cutlery handles. By the 1860s, the decimation of global elephant populations had driven ivory prices to unsustainable levels, creating a powerful market incentive for material innovation. It was this economic pressure that spurred the transition from the extraction of nature to the synthesis of matter. The scientific prologue to this industrial revolution occurred in London at the Great International Exhibition of 1862. Alexander Parkes, a metallurgist and inventor, displayed Parkesine, a material derived from cellulose treated with nitric acid and solvents. Parkesine was a marvel of the age, a man-made substance that could be molded when heated and retained its shape when cooled. It was, in effect, the world's first thermoplastic. However, Parkes failed to commercialize the invention effectively. The material was prone to warping and cracking, and production costs remained prohibitively high compared to rubber. Parkesine remained a scientific curiosity rather than an industrial reality, a testament to the difficulty of scaling polymer chemistry from the laboratory bench to the factory floor. The true industrial breakthrough arrived 6 years later in the United States, driven by a specific commercial bounty. The Phelan and Colander Billiard Supply Company, facing the ivory shortage, offered a $10,000 prize to anyone who could create a viable substitute for the billiard ball. John Wesley Hyatt, a printer from Albany, New York, took up the challenge. Building on Parkes's work but adding a crucial modification, Hyatt discovered that adding camphor, a derivative of the laurel tree, to cellulose nitrate under heat and pressure, created a stable, hard, and workable material. He named it celluloid. Celluloid was the first semi-synthetic plastic. It was not created from scratch, but a chemical modification of natural cellulose fibers, cotton or wood pulp. Despite its revolutionary moldability, it retained a dangerous flaw: high flammability. Yet its ability to mimic expensive natural materials like ivory, tortoiseshell, and linen allowed for the democratization of luxury goods. Combs, buttons, and collars once the province of the wealthy, could now be mass-produced for the growing middle class. The invention of the material was half the battle. The industrial method of processing it was equally critical. In 1872, John Wesley Hyatt and his brother Isaiah patented the first injection molding machine, U.S. Patent 133229. This device is the great ancestor of the massive manufacturing complexes of 2024. The patent describes a machine that was primitive by modern standards, but conceptually brilliant. It functioned similarly to a large hypodermic needle, utilizing a simple plunger mechanism to force molten celluloid through a heated cylinder into a two-part mold. The mechanics of this early machine revealed the limitations of the era. The stuffing cylinder was heated by a steam or hot water jacket designed to melt the camphor cellulose mixture. Then a hydraulic or mechanical plunger drove the material forward. However, the thermodynamics of this plunger system were fundamentally flawed for large-scale production. The heat was only applied from the outside walls of the cylinder. Plastic, being a poor conductor of heat, would often burn or degrade near the hot walls, while the center of the material mass remained cold and solid, a phenomenon known as the laminar flow problem. Consequently, the Hyatt machine was limited to producing small, simple items with thin walls, such as buttons, collar stays, and combs. It lacked the pressure generation and thermal homogeneity required for large, complex, or precision parts. Despite these limitations, the 1872 patent marked the birth of the plastics processing industry, establishing the fundamental principle of forcing a polymer melt into a closed cavity that remains the standard today. If celluloid was the prologue, Bakelite was the first chapter of the modern plastic age. By the turn of the 20th century, the industrial world was electrifying, and a new scarcity had emerged: a shortage of shellac, a natural resin secreted by the lac beetle, which was used to insulate electrical coils. The search for a synthetic shellac led Belgian chemist Leo Baekeland to his home laboratory in Yonkers, New York. In 1907, Baekeland successfully controlled the violent reaction between phenol, a coal tar derivative, and formaldehyde. Unlike cellulose, which was modified organic matter, the resulting material was entirely synthetic. It was a thermoset plastic. Once molded and heated, it formed a hard, irreversible chemical bond that would not melt. He named it Bakelite. The commercialization of Bakelite required the invention of new industrial hardware. The reaction between phenol and formaldehyde was temperamental. If not strictly controlled, it would foam into a useless, porous sponge. Baekeland developed the Bakelizer, a heavy iron steam pressure vessel approximately 1.5 meters, 4.9 feet tall. This vessel allowed for the precise regulation of heat and pressure, suppressing the release of gases during the reaction and ensuring a solid, dense resin. The economics of Bakelite were defined by the power of the patent monopoly. Baekeland filed his seminal patent in 1907, granted in 1909, and formed the General Bakelite Company in 1910. The material's properties, electrical non-conductivity, heat resistance, and chemical inertness, made it the foundational material for the Second Industrial Revolution. It replaced porcelain and shellac in high-voltage insulators, distributor caps for the burgeoning automobile industry, and casings for the new radio sets connecting the world. In 1922, the industry saw its first major consolidation. Following favorable patent litigation that solidified his control over the technology, Baekeland merged his General Bakelite Company with the Condensite Company and Redmanol Chemical Products to form the Bakelite Corporation. This merger created the first true giant of the plastics industry, establishing a business model of patent-protected technology and corporate consolidation that would define the sector for the next century. The age of Bakelite demonstrated that synthetic materials could essentially outperform natural counterparts in demanding industrial applications, justifying significant capital expenditure in chemical processing plants. While molding technology evolved in the United States, extrusion technology, the process of forcing material through a die to create continuous profiles like pipes or sheets, was developing in parallel in Europe. The roots of this technology lay in the rubber industry. In 1820, Thomas Hancock in England invented a masticator to reclaim rubber scraps, and in 1845, Henry Bewley designed an extruder for gutta percha, a natural latex used to insulate the first submarine telegraph cables. However, the application of extrusion to thermoplastics remained nascent until the 1930s. The early screw extruders were simple Archimedean screws designed to transport rubber, which required little melting. Adapting this for plastics required a fundamental rethink of thermodynamics. The screw had to not just transport the material, but compress and melt it through friction and shear. This technological gap would not be fully bridged until the eve of World War II, setting the stage for the massive industrial expansions to come. The War Machine and the Birth of Giants, 1930s to 1949. The 1930s and 1940s marked the transition of plastics from novelty items and electrical insulators to strategic geopolitical assets. As the clouds of World War II gathered, nations realized that access to natural raw materials, rubber from Southeast Asia, silk from Japan and China, bristles from Russia, could be severed by naval blockades. This realization drove the major powers to seek autarky, self-sufficiency, in critical materials, catalyzing the greatest government-sponsored industrial expansion in history. The chemistry of carbon became a matter of national survival. In the United States, the chemical giant E.I. DuPont de Nemours and Company, DuPont, sought to free the textile industry from its reliance on Japanese silk. Under the direction of Wallace Carothers, a brilliant organic chemist, DuPont's research team synthesized polyamide 6:6, trade-named nylon, in 1935. Nylon was the first fully synthetic fiber, stronger than silk and derived entirely from coal, air, and water. The commercialization of nylon required a financial gamble of unprecedented scale. In the midst of the Great Depression, DuPont authorized an investment of $27 million, approximately $600 million adjusted for 2024 inflation, to bring nylon to market. A significant portion of this, $8 million, was allocated for the construction of the world's first nylon plant in Seaford, Delaware. This single plant represented 1/6 of DuPont's entire net earnings for 1938, underscoring the immense capital risk involved. Construction at Seaford began in March 1939 and moved at a frantic pace, with the 6-story facility commencing operations just 9 months later in December 1939. The site was chosen for its proximity to the major textile markets of the Northeast and available raw materials. The technical challenges were immense. The spinning of molten polymer at high speeds required entirely new metallurgy and temperature controls. To prevent the hot polymer from oxidizing, the plant utilized a Seaford-grade nitrogen atmosphere, a level of purity previously unknown in industrial processing. The economic impact was immediate. In its first year, the Seaford plant produced 4 million pounds of fiber. As the war began, the plant's output was commandeered entirely for the military. The nylon capital of the world, as Seaford became known, ran 24 hours a day, producing material for parachutes, B-29 bomber tires, and mosquito netting. By the end of the era, capacity had expanded 100-fold to 400 million pounds, demonstrating the scalability of synthetic fiber production. While DuPont mastered polyamides, Imperial Chemical Industries in the United Kingdom stumbled upon the plastic that would become the most ubiquitous material of the 20th century, polyethylene. The discovery in 1933 at the Winnington Laboratory was a true accident. Chemists Eric Fassett and Reginald Gibson were experimenting with ethylene under extreme pressure, 1,700 atmospheres, when a leak in the vessel introduced trace amounts of oxygen. This oxygen acted as a catalyst, polymerizing the gas into a white, waxy solid. Scaling this high-pressure synthesis was fraught with danger. The reaction was exothermic and prone to explosive decomposition. However, the looming war accelerated development. ICI built the first pilot plant in 1937 and a full-scale commercial unit in 1939. The timing was providential. Polyethylene possessed exceptional dielectric properties, making it an ideal insulator for ultra-high-frequency UHF radar cables. Unlike previous insulators, it was lightweight and flexible. This material became a British state secret. It allowed the Allies to install radar systems in aircraft that were significantly lighter and more compact than German equivalents, providing a decisive tactical advantage in the Battle of Britain and the Battle of the Atlantic. While the Germans had superior rocketry, the Allies had superior plastics. The most dramatic chapter of industrial plastic history is the race for synthetic rubber. Natural rubber, harvested primarily in Southeast Asia, was the Achilles heel of mechanized warfare, vital for tires, tank treads, and seals. When Japan occupied the rubber-producing regions of Malaya and the Dutch East Indies in 1942, cutting off 90% of the U.S. supply, the Allied war effort faced immediate collapse. Germany, anticipating a blockade, had prepared for this vulnerability. Under the Nazi policy of autarky, the chemical conglomerate IG Farben invested heavily in Buna rubber, styrene butadiene rubber. By 1941, Germany was already producing 70,000 tons of synthetic rubber annually at massive industrial complexes like Schkopau and Hewells. These plants were marvels of chemical engineering, but were built on a sinister economic foundation, often utilizing forced labor. The U.S. response to the rubber crisis was an industrial mobilization rivaling the Manhattan Project in scale and complexity. In 1941, the U.S. produced a negligible 231 tons of synthetic rubber. The Rubber Reserve Company was formed, and the U.S. government invested approximately $700 million, over $13 billion in 2024 dollars, to build 51 government-owned, contractor-operated plants. This program required the forced collaboration of fierce competitors, Firestone, Goodrich, Goodyear, and U.S. Rubber, who were compelled to share patents and processes to standardize the GRS formula. The results were staggering. Production skyrocketed from 3,721 tons in 1942 to 756,000 tons in 1945. By the end of the war, the U.S. had built an entire synthetic rubber industry from scratch, surpassing the German output by an order of magnitude. As the war ended, the industry faced a unique challenge. The massive capacity built for explosives, which used cellulose nitrates, and radar insulation, polyethylene, needed new markets. However, the processing technology had lagged behind the material science. The old plunger injection molding machines could not efficiently process the new, more sensitive materials like PVC and the heat-sensitive nylons at high speeds. The laminar flow problem resulted in uneven heating and slow cycle times, creating a bottleneck for mass production. In 1946, American inventor James Watson Hendry revolutionized the industry by inventing the reciprocating screw injection molding machine. This invention was the mechanical key that unlocked the age of mass disposability. Instead of a simple plunger, Hendry employed a rotating screw inside the heated barrel. As the screw turned, it churned the plastic pellets, creating friction heat or shear heating that melted the material more uniformly than external heaters ever could. The screw also acted as a ram. Once the material was molten, the entire screw plunged forward to inject the shot. With this design, the cold core issues of plunger machines were eliminated, and with pigments could be mixed directly in the barrel, the vibrant colors that would define 1950s consumer goods obtained. Also, cycle times were drastically reduced, lowering the unit cost of production to levels where disposability became economically viable. It is estimated that 95% of modern injection molding machines still operate on this fundamental principle. The age of disposability and the petrochemical boom, 1950s to 1990s. The post-war era witnessed the swords to plowshares conversion of the chemical industry. The facilities that had produced nitrates for bombs and polyethylene for radar were retooled to feed a burgeoning consumer society. This era is defined by the fundamental shift in feedstocks, from the coal tar chemistry of the early 20th century to the cheaper, more abundant oil and natural gas liquids of the petroleum age. This golden age of petrochemicals saw plastic production grow from 1.5 million tons in 1950 to over 200 million tons by the turn of the millennium. The cultural shift toward disposability was physically enabled by advancements in blow molding, a technology that allowed plastic to challenge glass and metal in the packaging market. The concept of blow molding was adapted from ancient glass blowing techniques. The first machinery for plastic blow molding was developed by Enoch Ferngren and William Kopitke of the Plax Corporation in 1938. Their early attempts utilized cellulose acetate, but the process remained niche due to the material's cost and brittleness. The catalyst for the revolution was the commercial availability of low-density polyethylene, LDPE, after the war. LDPE was chemically resistant, non-toxic, and crucially, flexible. The first major commercial proof of concept was the Stop-At deodorant spray bottle, molded by Plax Corp in the late 1940s. The success of the squeeze bottle proved that consumers preferred the lightweight, unbreakable nature of plastic over glass. The industry took another quantum leap in the early 1950s with the discovery of high-density polyethylene, HDPE, by Phillips Petroleum in the US and Carl Ziegler in Germany. HDPE was stiffer and stronger than LDPE, allowing for lighter, thinner-walled containers that could stack. By 1960, blow-molded HDPE bottles began replacing heavy glass jugs for bleach and detergent. This substitution sparked a massive demand for polyethylene resin, driving the construction of vast petrochemical complexes along the U.S. Gulf Coast and in Western Europe. Technological sophistication increased rapidly. In 1949, Reinhold Hagen of Kautex Werke in Germany developed the first commercially available blow molding equipment for polyethylene. Later, Japanese and German engineers pioneered 3D blow molding, enabling the production of complex, irregular shapes like automotive air ducts and fuel tanks, further displacing metal in industrial applications. The petrochemical industry, having tethered itself entirely to oil and gas feedstocks, faced its first existential crisis during the oil shocks of 1973 and 1979. The 1973 OAPEC embargo caused oil prices to quadruple from $3 to nearly $12 per barrel. Since naphtha, a derivative of crude oil, was the primary feedstock for European and Asian plastic production, the cost basis of the industry evaporated overnight. The Producer Price Index for plastic resins and materials in the U.S. spiked dramatically, breaking the decades-long trend of falling prices driven by economies of scale. The high cost of resin forced the industry to innovate for efficiency. Manufacturers developed stronger resin grades that allowed for thinner walls in bottles and packaging to save material. In the 1970s, James Watson Hendry, the father of the reciprocating screw, introduced gas-assisted injection molding. By injecting nitrogen gas into the mold cavity, manufacturers could create hollow channels within thick parts. This reduced the weight of the part and the cooling time required, creating significant material savings and cycle time improvements. To process recycled and hygroscopic materials without expensive pre-drying, vented extruders were developed in the 1960s and widely adopted in the 1970s. This technology allowed volatiles to escape during the melt phase, improving the quality of cheaper, lower-grade resins. Until the 1970s, global plastic production was an Atlantic hegemony, dominated by the United States and Western Europe. The 1980s marked the beginning of the pivot to the Pacific. Japan leveraged its booming consumer electronics and automotive sectors to become a leader in high-precision molding. Companies like JSW and Fanuc began exporting advanced machinery that challenged Western dominance. JSW, for instance, developed large-scale twin-screw extruders essential for the burgeoning polyolefin industry and pioneered all-electric injection molding machines in the 1980s. These electric machines replaced hydraulic systems with servo motors, offering superior precision and energy efficiency, a critical selling point in a post-oil shock world. Between 1980 and 2000, global plastic production more than tripled, rising from approximately 70 million tons to 234 million tons. A significant portion of this new capacity was installed in Asia. The four Asian tigers, South Korea, Taiwan, Hong Kong, and Singapore, and subsequently China, began to absorb the world's demand for commodity manufacturing. By 2000, Asia's share of global plastic production had risen to 35%, up from less than 5% in 1950. While injection molding dominated durable goods, thermoforming, vacuum forming, captured the single-use packaging market. The development of the roll-fed thermoforming machine by C.B. Strouch in 1938 had laid the groundwork, but the 1980s and 90s saw the explosion of this technology for blister packs, yogurt cups, and clamshell containers. This low-cost, high-speed process was the final piece of the puzzle for the age of disposability, enabling the cheap packaging of everything from electronics to fast food. The modern high-performance era, 2000s to present. The turn of the millennium brought a bifurcation in the industry. The market split into two distinct economic realities: a commoditized, high-volume market for standard resins, PE, PP, PVC, characterized by razor-thin margins and Asian dominance, and a high-margin, lower-volume market for advanced engineering polymers and composites. As commodity plastics became cheaper, Western chemical companies retreated up the value chain, focusing on high-performance polymers that could survive in environments previously reserved for metals. Developed by ICI in 1978 and commercialized as Victrex in the early 1980s, PEEK became the gold standard for high-temperature applications. It retains its mechanical properties at temperatures up to 260 degrees Celsius, 500 degrees Fahrenheit, far beyond the melting point of standard plastics. In the 2000s, as original patents expired, new entrants like Solvay and Evonik entered the market, expanding supply. PEEK is now critical in aerospace and medical sectors, used to replace titanium in spinal implants and aluminum in aircraft brackets due to its radiolucency and high strength-to-weight ratio. The market for carbon fiber reinforced polymers, CFRP, evolved from a niche aerospace material to a strategic industrial sector. Valued at $2.81 billion in 2024 and projected to reach over $10 billion by 2030, this market is driven by the wind energy sector for massive turbine blades and the light weighting requirements of electric vehicles. The industrialization of carbon fiber represents the ultimate maturation of the polymer age, a plastic material that is stronger and stiffer than steel. A geopolitical inversion occurred in the 2010s with the U.S. shale gas boom. Historically, the U.S. chemical industry relied on natural gas liquids, ethane, for feedstock, while Europe and Asia relied on oil-derived naphtha. When oil prices were high, 2010 to 2014, and U.S. natural gas prices plummeted due to fracking, U.S. polyethylene became significantly cheaper to produce than its Asian or European counterparts. This cost advantage triggered a massive wave of capital expenditure in the U.S. Gulf Coast. Billions of dollars were invested in new ethane crackers and derivative plants by companies like Dow, ExxonMobil, and Chevron Phillips, aiming to export cost-advantaged polyethylene pellets to the hungry markets of Asia. China, the world's largest consumer of plastics, responded to its import dependence with the Made in China 2025 strategic initiative. This state-led policy aimed to transform China from the world's factory, assembling imported components, into a self-sufficient industrial superpower. The plan set explicit targets, such as achieving 70% self-sufficiency in core basic materials by 2025. China aggressively expanded its domestic capacity for upstream chemicals, paraxylene, ethylene, propylene. By 2024, China accounted for nearly 47% of global chemical investment, a staggering figure that dwarfs the investment of all other regions combined. This massive capacity buildup has led to a structural oversupply in the global market by 2024-2025. The flood of new Chinese capacity has depressed global prices for commodity resins like polypropylene and PVC, squeezing margins for producers in Europe and South Korea. Industrial and financial analysis. The trajectory of plastic production describes an exponential curve that has proven remarkably resilient to global economic recessions. The geography of investment tells the story of the industry's future. In the 1990s, CapEx was relatively balanced between NAFTA, Western Europe, and Japan, reflecting a tripolar industrial world. In the 2010s, the U.S. shale boom attracted approximately $200 billion in petrochemical investments to the Gulf Coast, revitalizing a mature market. In 2020s, China dominates the investment landscape. In 2024, China's chemical capital spending represented nearly half of the global total. The state is building mega refineries that integrate crude oil processing directly into chemical production, bypassing traditional fuel production to maximize petrochemical yield. The correlation between oil prices and resin prices has evolved from a direct linkage to a more complex relationship defined by regional feedstock decoupled. In 1970s to 1980s, the oil shocks caused direct, immediate inflation in plastic prices. Polyethylene prices mirrored crude oil spikes because the entire industry was effectively indexed to the price of a barrel of oil. In 2020s, a significant decoupling is emerging due to structural overcapacity. Despite crude oil prices hovering around $70 to $80 per barrel in 2024, prices for polypropylene and PVC have faced severe downward pressure. This is driven by the glut of supply from new Chinese plants coming online regardless of immediate demand signals. For instance, polypropylene prices in 2025 are forecast to decline across North America and Asia due to massive capacity expansion in China outpacing global consumption growth. Evolution of production technologies. Injection molding. In 1872, Hyatt invented the plunger, characterized by low pressure and thermal unevenness, suitable only for small, simple parts. In 1946, Hendry invented the reciprocating screw. The industry standard enabled homogeneous melting and high-speed cycles. In 1970s, Hendry introduced gas-assisted, allowed for the molding of large hollow parts like automotive handles and furniture, saving material and weight. In 1980s, all-electric machines pioneered by Japanese firms like JSW and Fanuc. These machines eliminated hydraulic oil, offering clean room compatibility, crucial for medical molding, and energy savings of 30 to 60%. In 2020s, decoupled molding and AI are developing. Modern systems use sensors inside the mold cavity to control the process in real time, adjusting pressure and temperature millisecond by millisecond to ensure zero-defect production. Extrusion. In 1930s, Colombo and Pesquetti developed the twin-screw extruder, a critical innovation that used two intermeshing screws. This provided the high shear and mixing capability necessary for compounding additives, pigments, and reinforcements into plastics, essential for modern PVC and master batch production. In 1959, the Matic mixer was a breakthrough in screw geometry developed by Union Carbide engineer B.H. Matic, which separated the solid bed of pellets from the melt pool, vastly improving the quality and output of single-screw extruders. Today, high-speed, high-torque twin-screw extruders are now the workhorses of the compounding industry, necessary for creating complex alloys like conductive plastics for EV batteries. Regional case studies in industrial policy. Germany's chemical prowess, embodied by giants like BASF, Bayer, and Hoechst, was forged in the existential necessity of two world wars. The ersatz substitute programs demonstrated to the world that synthetic materials could sustain a modern war economy. This legacy transitioned in the post-war era into a dominance in high-performance engineering plastics and processing machinery. German machine builders, for example Arberg, Cross-Maffei, Battenfeld, remained global leaders in high-end equipment, exporting the picks and shovels of the plastic age to the rest of the world. The U.S. trajectory is defined by corporate R&D giants DuPont, Dow, Monsanto, transitioning to feedstock-advantaged commodity producers. The U.S. government's $700 million investment in synthetic rubber during WWI remains the historical benchmark for successful state-sponsored industrial policy. Today, the U.S. leverages its shale gas advantage to remain a low-cost producer of polyethylene, even as it innovates in bioplastics and advanced composites. Made in China 2025 represents the state's intent to move up the value chain from assembly to synthesis. China is no longer just the world's molder, processing imported resin, it is becoming the world's refiner. China has successfully reduced its import dependency for key resins like polypropylene and PET, fundamentally altering global trade flows. While still importing some specialized high-end polymers, China is aggressively pursuing leadership in green manufacturing and new materials, supported by a massive domestic market and state-directed capital. The history of the plastics industry is a mirror of the industrial age itself. It began with the Victorian desire to mimic nature, ivory, matured through the existential military needs of the mid-20th century, rubber and nylon, and exploded during the post-war consumerist boom. Technologically, the industry moved from the crude mechanics of the steam-heated plunger to the precision of the reciprocating screw and the digital control of modern electric machines. Economically, it has shifted from a high-margin, patent-protected Western monopoly to a hyper-competitive, globalized commodity market where Asian capacity dictates price. As we move through the 2020s, the industry faces its fourth age, sustainability. With production projected to triple by 2060 under business-as-usual scenarios, the next great industrial evolution will likely not be a new polymer, but a new process, chemical recycling and circularity, compelled by the same force that started it all in 1860, the scarcity of resources and the necessity of adaptation. The Petro-Plastic Nexus, Feedstocks, Fracking, and the Geopolitics of Ethane. The plastic industry does not exist in an industrial vacuum. It is the chemical offspring and the economic lifeline of the oil and gas industry. The integration between these two sectors is absolute, with petrochemicals serving as a primary driver for future oil demand, even as the global energy matrix attempts a tentative transition away from fossil fuels for combustion-based power generation. To comprehend the economics of plastic, one must first comprehend the economics of the hydrocarbon molecule and the infrastructure built to manipulate it. At its most fundamental level, the petrochemical industry is an apparatus of transformation dedicated to converting raw materials derived from crude oil and natural gas into a vast array of chemicals and products that underpin the functionality of modern life. These raw materials, known in the industry as feedstocks, are the decisive factor in the economics, geographical location, and environmental footprint of plastic production. The industry bifurcates its feedstock sources into two primary categories, each with distinct economic implications. Light feedstocks, natural gas liquids. This category includes gases such as ethane, propane, and butane. These are primarily derived from natural gas processing and the separation of natural gas liquids. Ethane is the most critical of these for the plastic sector, because through the process of steam cracking, it yields a high percentage of ethylene, the monomer building block for polyethylene, the world's most ubiquitous plastic. Heavy feedstocks, crude oil derivatives, encompasses naphtha, gas oil, and other heavier liquid fractions derived from the refining of crude oil. Naphtha cracking is historically dominant in regions like Europe and Asia that lack abundant natural gas reserves. While naphtha cracking produces ethylene, it also yields a wider variety of co-products, including propylene, butadiene, and aromatics, benzene, toluene, xylene, which are essential for producing other polymers like polypropylene, polystyrene, and synthetic rubbers. The economic integration of these sectors is driven by the crack spread, the differential between the cost of the raw feedstock and the market price of the resulting petrochemicals. Historically, the global market saw regional specialization. The Middle East, with its vast associated gas reserves, dominated ethane-based production, while Europe and Asia relied on oil-based naphtha. However, the 21st century introduced a disruptive variable that realigned this geopolitical map: the U.S. shale revolution. The most significant geopolitical shift in the modern plastics industry was precipitated by the U.S. shale gas boom. The advent and widespread deployment of hydraulic fracturing, fracking, and horizontal drilling technologies unlocked vast, previously inaccessible reserves of natural gas and NGLs in geological formations such as the Marcellus and Utica shales. This extraction boom created a massive surplus of ethane, a byproduct that was previously so abundant relative to infrastructure capacity that it was often rejected, left in the natural gas stream and sold at its heating value, or flared off at the wellhead. This surplus fundamentally altered the cost structure of global plastic production, creating a distinct ethane advantage for North American producers. Historically, the price of natural gas and oil moved in relative tandem. The shale boom caused a decoupling. U.S. natural gas prices plummeted due to oversupply, while global oil prices remained relatively high. This made ethane-based ethylene production significantly cheaper than naphtha-based production in oil-dependent regions. In September 2012, for example, the cost to produce a pound of ethylene using ethane feedstock in the United States was approximately 60 cents. In contrast, producing that same pound of ethylene using naphtha in oil-dependent regions cost $1.37. This five-fold divergence in feedstock costs between May 2011 and September 2012 effectively monetized the U.S. competitive advantage, rendering American polyethylene highly profitable while placing immense pressure on European and Asian competitors. This cost disparity triggered a massive wave of capital investment concentrated along the U.S. Gulf Coast and increasingly in Appalachia near the shale plays. Petrochemical giants, including foreign firms, rushed to construct ethane crackers, massive industrial flagellators capable of heating ethane to temperatures exceeding 1,500 degrees Fahrenheit to break its molecular bonds. By 2017, the United States had re-emerged as a global low-cost superpower for chemical production, second only to the Middle East. Ethane cracking capacity in the U.S. expanded by nearly 33%, transforming the nation from a net importer of plastics into a dominant global exporter, aggressively targeting high-growth markets in China, Europe, and Latin America. The physical manifestation of this economic integration is best exemplified by the colossal integrated complexes that dot the Gulf Coast, most notably the ExxonMobil facility in Baytown, Texas. Founded in 1919, this 3,400-acre industrial city along the Houston Ship Channel represents the pinnacle of vertical integration, where the boundary between oil company and plastics manufacturer dissolves. The Baytown complex illustrates the seamless industrial flow from fossil fuel extraction to finished polymer. The Baytown refinery, one of the largest in the United States, processes up to 584,000 barrels of crude oil per day. It produces fuels, but critically, it generates the feedstocks required for chemical synthesis. The adjacent Baytown Olefins plant takes these refinery feedstocks, along with natural gas liquids piped in from shale fields, to produce approximately 10 billion pounds of petrochemicals annually. It is a feedstock-flexible plant, capable of oscillating between ethane and naphtha depending on market arbitrage, insulating the operator from volatility. These basic chemicals, ethylene, propylene, butadiene, are piped directly to the on-site chemical plant and the nearby Mont Belvieu plastics plant. Here, they are polymerized into polyethylene for packaging, polypropylene for automotive parts, and butyl rubber for tires. In a strategic pivot towards future sustainability mandates, Baytown has recently integrated advanced recycling facilities. Using proprietary Extend technology, the complex now processes over 80 million pounds of hard-to-recycle plastic waste annually, breaking polymers back down into molecular feedstocks to be re-fed into the production system, an attempt to close the loop within the existing petrochemical infrastructure. As the transportation sector slowly begins to electrify and internal combustion engine efficiency improves, the oil industry is increasingly identifying petrochemicals as its primary engine of future growth. The International Energy Agency reports that petrochemicals are set to account for more than a third of the growth in global oil demand to 2030 and nearly half to 2050, surpassing the combined demand growth of trucks, aviation, and shipping. This petrochemical transition implies that even in a decarbonizing world, the extraction of fossil fuels will remain robust, shifting the end use from combustion, energy release, to material production, carbon sequestration in solid form. This creates a complex paradox. While the global community seeks to reduce carbon emissions from burning fuels, it is simultaneously increasing its dependence on the carbon atoms contained in plastics, fertilizers, and synthetic textiles. The lock-in effect of this infrastructure, billions of dollars invested in crackers with operational lifespans of decades, ensures that the flow of ethane and naphtha into the plastics economy will continue to be a dominant force in global energy markets for the foreseeable future. The material revolution, reshaping everyday life and social fabric. The transition from natural materials to synthetics in the mid-20th century was not merely a material substitution, it was a fundamental transformation of the capabilities of human civilization. Plastic did not just replace wood, glass, and metal, it enabled entirely new forms of living, altering the mechanics of hygiene, the logistics of food preservation, and the sociology of domestic labor. Perhaps no sector has been as profoundly transformed by plastic as healthcare. The shift from glass and metal instruments to disposable plastic devices represents a monumental leap in global public health, specifically regarding sterility and disease prevention. Prior to the 1950s, the hypodermic syringe was a durable asset crafted from glass and metal. The Pravaz and Luer syringes were valuable instruments that required rigorous maintenance. After every single use, a syringe had to be disassembled, cleaned, the needle sharpened, and then sterilized by voiling or autoclaving. This workflow was labor-intensive, prone to human error, and carried a perpetual risk of cross-contamination. In mass immunization campaigns, the time required to sterilize needles between patients often led to lapses in protocol, contributing to the spread of hepatitis and other blood-borne pathogens. The revolution was driven by the convergence of mass vaccination needs and polymer engineering in the mid-1950s. In 1954, Becton Dickinson, BD, mass-produced the first disposable glass syringes for Dr. Jonas Salk's polio vaccination program. While still glass, this proved the logistical viability and safety benefits of the single-use model. New Zealand pharmacist Colin Murdoch, observing the risks inherent in reusable glass, patented the disposable plastic syringe. Inspired by the mechanism of a fountain pen, he designed a unit with a free-moving piston within a plastic chamber. It was cheap to mold, pre-sterilized by gamma radiation, and designed to be incinerated after a single use. BD introduced the Plastipack in 1961, cementing the plastic syringe as the industry standard. This innovation virtually eliminated patient-to-patient infection via needle reuse in developed nations and drastically reduced the logistical burden on hospital staff. Today, the healthcare sector relies on the single-use model for everything from IV fluid bags and catheters to surgical gowns and ventilator tubes. While this has created a significant biohazardous waste stream, the trade-off has been a massive reduction in nosocomial infections and the ability to deliver complex therapies like dialysis and chemotherapy that require absolute sterility. In the post-war era, plastic entered the home, reshaping the American kitchen and the social lives of women. The most iconic agent of this change was Tupperware, a product line that became a cultural phenomenon. Invented by Earl Tupper in the 1940s, Tupperware utilized polyethylene, a slag byproduct of oil refining that was refined during WWI-2 for radar insulation, to create airtight, flexible food containers. The patented burping seal promised to keep food fresh significantly longer than ceramic or glass, revolutionizing food preservation in an era before the universal efficiency of modern refrigeration. However, the true revolution was social. Brownie Wise, a charismatic sales executive, realized that Tupperware required demonstration to be sold effectively. Consumers needed to learn how to burp the seal. She pioneered the Tupperware Party, a direct sales model that leveraged women's existing social networks. For the 1950s housewife, Tupperware offered a rare avenue for economic independence. It allowed women to earn a substantial income without neglecting their domestic duties, as the work took place in the domestic sphere, either their own home or a neighbor's. Brownie Wise became the first woman to appear on the cover of Business Week, symbolizing this new female entrepreneurial power. Critics and historians note the double-edged nature of this phenomenon. While it provided income, the Tupperware model reinforced the ideology that a woman's primary domain was the home. It monetized female friendship and kept women's labor focused on kitchen efficiency rather than facilitating their entry into the broader public workforce. The cultural pivot from reuse to dispose was not an accidental byproduct of plastic. It was an engineered cultural shift. In August 1955, Life magazine published a landmark article titled "Throwaway Living," featuring a photo of a family gleefully tossing disposable plates, cups, and napkins into the air. The caption celebrated that these items would take 40 hours to clean, but now no housewife need bother. Until the 1960s, milk was delivered in reusable glass bottles, which were heavy, breakable, and required a reverse logistics network for collection and washing. The introduction of high-density polyethylene jugs replaced these containers. HDPE was lighter, reducing transport fuel costs, and shifted the disposal responsibility to the consumer, eliminating the dairy's need to manage return logistics. The PET, polyethylene terephthalate bottle, patented in 1973, revolutionized the soft drink industry. It was shatterproof and lightweight, allowing for larger sizes like the 2-liter bottle that glass could not safely support. By the 1980s, plastic had become the dominant packaging material for water and soda, firmly establishing the throwaway society, where durability was replaced by convenience and the life cycle of a product was decoupled from its utility. Plastic in the cultural imagination, semiotics, cinema, and dystopia. As plastic saturated the material world, it inevitably seeped into the collective consciousness. In literature, film, and philosophy, plastic became a powerful metaphor for artificiality, malleability, and the anxieties of the modern age. In his seminal 1957 collection, Mythologies, French semiotician Roland Barthes dedicated an essay to plastic, capturing the mid-century awe of the material. For Barthes, plastic was a magical substance that embodied the transformative power of modern industry. Barthes described plastic not as a material, but as the very idea of its infinite transformation. He marveled at the machine that takes raw, telluric matter, oil or slime, and excretes a finished, shiny object. It was a secular miracle, an alchemy that turned sludge into jewels or buckets. Barthes presciently noted that the whole world can be plasticized. He observed that unlike wood or metal, which have inherent qualities and histories, plastic is a disgraced material. It has no essence, only the ability to imitate. It represents the triumph of function over substance. He characterized plastic as less a thing than the trace of a movement, emphasizing its state of becoming. It is the physical manifestation of the fluidity of modern capital and mass production. 10 years after Barthes, the cultural mood shifted. In Mike Nichols' film The Graduate, a single line of dialogue encapsulated the generational divide and the growing cynicism toward American materialism. At his graduation party, the protagonist, Benjamin Braddock, Dustin Hoffman, is cornered by Mr. McGuire, a friend of his parents. McGuire offers career advice. "I just want to say one word to you. Just one word. Plastics." To McGuire, plastics represents a booming industry, a ground floor economic opportunity. To Benjamin and the 1960s counterculture audience, plastics is a metonym for everything phony, superficial, and manufactured about his parents' suburban existence. The line marks the moment when plastic became an insult. To be plastic was to be fake, rigid, and soulless. The film uses the material to symbolize a future that is economically secure but spiritually void. This moment is widely cited as one of the most famous lines in movie history, crystallizing the rejection of the throwaway living ethos by the burgeoning environmental and youth movements. In the 1980s, the cyberpunk genre, pioneered by William Gibson, reclaimed plastic not as a symbol of sterile suburbia, but as the gritty texture of a high-tech, low-life future. In Gibson's Sprawl, nature is dead or paved over, and the world is composed of synthetic surfaces. Gibson describes the sky as the color of television, tuned to a dead channel. The environment is littered with crumpled plastic film and foam packing units. Cyberpunk extends Barth's idea of plasticized life to the human body itself. Characters modify themselves with cheap pink plastic prosthetics and carbon sockets. Plastic is no longer just packaging, it is flesh. The plastic nature of the world reflects the plasticity of reality in cyberspace. Just as plastic can be molded into any shape, the digital world allows for the infinite reshaping of identity and environment. Gibson's constellation of cheap chrome and rainbow surface like oil on water aestheticizes the pollution and synthetic decay of the post-industrial world. The anxiety over society's total dependence on synthetic materials found its voice in the 1971 novel Mutant 59, The Plastic Eaters, by Kit Pedler and Jerry Davis. A bacterium engineered to digest plastic waste escapes into London. It does not attack humans directly, it attacks the infrastructure. It melts insulation off wires, causing subway fires, dissolves gas pipe seals, causing explosions, and liquefies airplanes in mid-flight. The novel illustrates the fragility of modern civilization. By 1971, the world was so thoroughly integrated with plastic that the removal of the material meant the collapse of society. It serves as a grim counter-narrative to Life magazine's throwaway living. The very durability that causes pollution is also the only thing holding the technosphere together. The narrative of plastic has recently shifted from visible litter to invisible contamination, centered on the concept of microplastics. The term microplastics was formally introduced and popularized in 2004 by Professor Richard Thompson, a marine biologist at the University of Plymouth. Though reports of plastic pellets, nurdles, in the ocean date back to the 1970s. In 2017, the BBC series Blue Planet 2, narrated by David Attenborough, featured footage of albatrosses feeding plastic to their chicks. The emotional impact triggered the Blue Planet effect. In the UK, it led to an immediate spike in search traffic for plastic recycling and ocean pollution, and influenced government policy bans on single-use items, marking the end of the miracle material narrative and the beginning of the toxicant narrative. Beyond the disposable, the rise of advanced composites, carbon fiber. While commodity plastics, packaging, disposables face public backlash, a different class of polymer composites is quietly revolutionizing high-performance engineering. Carbon fiber reinforced polymer, or CFRP, represents the high-tech evolution of the industry, where the focus is not on cheap disposability, but on extreme durability and strength-to-weight efficiency. Carbon fiber is produced by oxidizing and carbonizing precursor fibers, usually polyacrylonitrile or PAN, at high temperatures until they are composed almost entirely of carbon atoms. These fibers are then woven into a fabric and embedded in a polymer matrix, usually epoxy. CFRP is up to 10 times stronger than steel by weight. It is roughly 1/5 the weight of steel and lighter than aluminum. Unlike metals, it does not corrode, making it ideal for harsh environments. To utilize CFRP, specialized manufacturing processes are required. Continuous fibers are wound around a rotating mandrel. This is the standard for creating cylindrical shapes like pressure vessels and pipes. The fibers can be wet, dipped in resin during winding, or toe preg, pre-impregnated with resin. For complex shapes like aircraft fuselages, robotic arms place bands of pre-preg tape onto a mold. This allows for precise control of fiber orientation, optimizing strength exactly where it is needed, and reducing waste compared to manual layup. The transition to a hydrogen economy is physically impossible without advanced composites. Storing hydrogen gas requires immense pressure, typically 700 bar, approximately 10,000 psi, to achieve sufficient energy density for vehicles. The industry standard for hydrogen storage is the Type 4 tank. It consists of a polymer liner, usually HDPE, to hold the gas barrier, and a fully overwrapped outer shell of carbon fiber to withstand the pressure, the structural load. Metals are too heavy and prone to hydrogen embrittlement. Only carbon fiber provides the necessary tensile strength to contain 700 bar pressure while keeping the tank light enough for a vehicle. Approximately 10 kilograms of carbon fiber is required to store just 1 kilogram of hydrogen. Companies like Semiotics and Voigt are pioneering toe-preg winding and fiber patch placement to reinforce the dome ends of tanks more efficiently, reducing carbon fiber usage by up to 15% and lowering costs, a critical step for making hydrogen vehicles commercially viable. The emerging electric vertical takeoff and landing (eVTOL) sector, flying cars, is entirely dependent on the weight savings provided by composites. A leader in this space, Joby Aviation has signed long-term supply agreements with Toray Advanced Composites. Their aircraft, the S-4, is designed to carry a pilot and 4 passengers up to 150 miles. Batteries have low energy density compared to jet fuel. To compensate for the heavy battery pack, the airframe must be exceptionally light. Toray supplies high-modulus carbon fiber prepregs that are used in the fuselage and propulsion systems. Every gram saved by using CFRP translates directly to increased range and payload. Unlike traditional aerospace, which builds small numbers of aircraft, the eVTOL market aims for automotive-scale production. This requires moving from manual layup to high-speed automated fiber placement, or AFP, to produce thousands of airframes annually. In the world of civil engineering, CFRP is replacing steel for retrofitting aging infrastructure. The Michigan Department of Transportation, or MDOT, has been a pioneer in this field. Steel reinforcement bars, or rebar, inside concrete bridges rust when exposed to water and de-icing salts, expanding and causing the concrete to crack and spall. MDOT uses carbon fiber strands for pre-stressing concrete beams. Since carbon fiber does not rust, these bridges have a theoretical lifespan of 100 years with minimal maintenance. A notable example is the Bridge Street Bridge in Southfield, Michigan, built 2001, the first in the country to use CFRP pre-stressing. More recently, MDOT deployed 140-foot carbon fiber beams on the I-75 span over the Sexton-Kilfoyle Drain. Beyond new builds, CFRP patches or wraps are used to repair damaged girders. For bridges hit by overheight trucks, applying CFRP laminates can restore the structural capacity to levels higher than the original undamaged girder, avoiding the massive cost of bridge replacement. The trajectory of the plastic industry describes an arc from miracle to menace, and finally to essential utility. In the early 20th century, plastic was the alchemical dream, a way to create abundance from scarcity, replacing ivory and tortoiseshell with celluloid and bakelite. In the mid-century, it became the domestic liberator and oppressor, enabling the hygiene of the disposable syringe and the convenience of Tupperware, while simultaneously trapping consumers in a cycle of throwaway living and gendered domestic expectations. In the late 20th century, it became the cultural villain, the symbol of phoniness in The Graduate and the texture of ecological collapse in Mutant 59 and Blue Planet 2. Today, we stand at a new juncture. the commodity plastics sector faces an existential crisis of waste, driven by the very cheapness that made it successful. Yet, simultaneously, the advanced composites sector, carbon fiber, is becoming the backbone of the green future. We cannot have hydrogen vehicles, efficient electric aircraft, or long-lasting infrastructure without these high-performance polymers. The plastic age is not ending, it is bifurcating. On one side, a struggle to defossilize and recycle the single-use economy. On the other, a high-tech acceleration into composites that are lighter, stronger, and more permanent than anything nature ever devised. The one word from The Graduate remains the key to the future, but its meaning has become infinitely more complex.